Today, we are kind of picking up a little bit. We focused mainly in lesson 6.1 with respect to kind of introducing exponential and logarithmic functions. Today, we're going to dive a little bit deeper, specifically into properties of logarithmic functions. I find them to be really fascinating, to be honest. They're kind of like a little puzzle, if you will. I grabbed a couple of items from yesterday's notes because they kind of bleed into what we're doing today. We learned from lesson 6.1 that exponential and logarithmic functions are inverses of one another. That first bullet point tells us that we can transform from an exponential function into a logarithmic function pretty easily. The second and third bullets were other properties for how we can rewrite when we have bases that are the same when we're simplifying. We also learned that by the graph of our functions that they were both one-to-one, and because they are one-to-one, we are able to find their inverses, which of course are the inverses themselves. What's an important property here that we're going to need when we start solving is the first bullet point in the bottom, that we're able, if we have the same bases and we raise them to the power, it doesn't matter what the base is, the powers have to be equivalent to one another. Similarly, if we have two log bases that are the same, what we can do is then set the in the middle part there, the u and w, equal to each other, and then the log bases don't matter. And that again will be very important when we start solving because it'll make our life a lot easier. So I'll refer back to this particular property when we start solving again in a couple of sections. Let's head over to slide 2. Here are some algebraic properties of exponential functions and logarithmic functions. I want to draw your attention specifically to the exponential properties of where we have the or part. I find these pieces, the way they're written, to be more easily understood than the ones with our function notation. Further, when I'm looking at algebraic properties of logarithmic functions, I want to draw your attention to the log part, so the second part, because I find those are the easiest ones to look at when we're actually simplifying. The product rule with exponential functions says, and we know this already, you've been doing that if you have the same base and you're multiplying the exponents, we actually add them together to combine into one. If we have the same base with our exponents, we subtract them when we are dividing. And if we have a power to a power, we multiply those powers together. Those are things and properties you've already been using. We're just kind of giving them a name when we're working with exponential functions in general. Logarithmic functions, I like to start on the inside here, that if we have two pieces being multiplied, we can expand them into adding the two logarithms together, one with u and one with w, whatever the two products are. Within the quotient rule, if we are dividing the pieces together, it's actually the same as subtraction. And then further, the quotient rule, when we have a power, we can use the power rule and bring that power in front of our logarithm, or vice versa. We're going to practice going back and forth with both of these, going from one to the other to simplify and or expand. So let's head over to slide 3 so we can actually get some of this to work for us. We'll start off with a basic example, and of course we're going to work our way and get more difficult as we go. We're going to assume when necessary that all quantities represent positive real numbers, since we assumed on the previous page that when x sometimes had to be greater than 0. So we're just going to assume in all instances that the quantities are positive real values when we're unsure if it's a variable. Here I have log base 2 of 8 over x. So I am dividing, which means that I can subtract the two logarithms. This would be the same then as saying log base 2 of 8 minus, since we're dividing, log base 2 of x. We can simplify log base 2 of 8, right? We did that in our lesson from yesterday. So I'm going to ask 2 times what power gives me 8. We know that 2 to the third power is 8. So therefore, this entire left-hand side is 3. This then would be 3 minus log base 2 of x, or we could write it as negative log base 2 of x plus 3, where you're putting the variable before the constant. Either one is okay. Let's head over to part B. We have log of 1/10 of 10x squared. The first thing I'm going to do is I'm going to expand this because I'm taking 10 times x squared here. I know that with x squared, I am able to use the product rule so I can break them apart into addition. So I'm going to start there. This is log base 1/10 of 10 plus, since it was the product rule, log of 1/10 of x squared. X squared. I then can use the power rule to take my 2 and bring it in front of my logarithm. Now I have log of 1/10 of 10 plus 2 times log of 1/10 of x. Now we might be able to simplify like we did in part A. All right, we have 1/10. I'm going to write that as a fraction, 1/10. That's why I've been saying it exactly how it's read. 1/10, and I should say 1/10 to what power is equal to positive 10? Well, I know that if I were to put a negative along with my 10, it would move it back up to the top. So 1 over 10 to the negative first power would give me 10 to the first power, which is ultimately equal to the 10 that's inside our parentheses. So therefore, log of 0.1 of 10 is negative 1 plus 2 log of 0.1x. Or again, if you want to put the variable first, 2 log base 1/10 of x minus 1. Many calculators for you obviously are able to evaluate. Desmos is also able to evaluate when we have bases. I'm going to tell you only evaluate and keep it if it's a nice whole number like the first 2 examples we've done. If it's an ugly decimal, leave it in its exact form. Leave it in its exact form. Okay. Looking at the natural log of 3 over e to ex all to the second power, we've got a lot of things going on. We have a power, we have some multiplication, and we have some division here. So let's start undoing this by utilizing the power rule. So I'm going to first take my 2 and bring it out front. This now will give us 2 times the natural log of 3 over ex. Now I'm going to use the quotient rule to undo the division. But keep in mind that 2 is being multiplied by the entire thing, right? 2 is times the entire thing. Even if I am expanding this to the natural log of 3 minus the natural log of ex, 2 is still being multiplied by that whole part. What we can do at this point is distribute the 2 through. So I have 2 times the natural log of 3, which I guarantee is going to be an ugly decimal if you plug that into the calculator. So I'm going to leave it in its exact form, minus 2 times the natural log of e times x. Now, e times x here is a product, so we can use the product rule in order to separate them apart. So I'll have 2 times the natural log of 3 minus 2 times all of this, the natural log of e, plus the natural log of x. I can also distribute so that I have 2 times the natural log of 3 minus 2 times the natural log of e, or Euler's number, minus 2 times the natural log of x. I will be able to simplify the natural log of e, and here's why. We're going to do a little side work. Recall from last lesson that the natural log is the same thing as saying log base e. And right now this is log base e of e. Remember that these almost, or I should rewrite it as an exponent here. So e, our base, to what power gives me the inside parenthesis, e? Well, we know that this is 1, so anything to the first power gives us what we need. Therefore, the natural log of e is simply 1. And 2 times 1 is still going to be negative 2 with that negative out front of it. So its final solution will be 2 times the natural log of 3 minus 2 times the natural log of x. You could also bring out that negative 2 natural log of x and put it out front. It doesn't matter to me how you write it if you just like to put your variables first and your constants second. Again, I'm going to leave 2 times the natural log of 3 in its exact form. Otherwise, it's going to be an ugly decimal, and it won't be exactly as we had it. So as you've probably noticed, our examples are getting a little more difficult as we go here. So the same is true with the next example. The cube root of 100 x squared over yz to the 5th. So we got lots of multiplication. We have ourselves a radical here. How the heck are we going to deal with that? And we've got division and multiplication all underneath of it. So this might take a little bit of time, but it certainly can be expanded pretty easily. So hang with me. I'm also going to erase some stuff here so that I have more room to write if we need it. I should have allowed myself more room, and I'll just change my color so it's easier to see. I'm going to rewrite my radical first because that's kind of the outermost piece that we have. We know that all of this here, if we're looking at it, is to the first power. So I'm going to turn this from a radical to an exponent by saying that this is the same as log, which is base 10, even though we don't see it, of 100 x squared over yz to the 5th to the power of 1/3. So the inside number, our exponent, goes on the numerator and the index is the denominator. Then I'm going to utilize my power rule to bring the 1/3 to the front of my logarithm. So then I'm done with the exponent itself for now. This is then 1/3 times log of x squared, over, sorry, I was going to do multiple steps at once. I don't want to do that to you yet, of 100 x squared over yz to the 5th. The next step I'm going to do, just like in part C, once we moved the exponent to the outside, I'm going to undo the division by writing this as a subtraction problem. This is then equal to 1/3 times log of 100 x squared minus log yz to the 5th. Since I have a lot of things happening on the inside here, I'm going to rewrite this a couple of ways. I'm going to kind of combine a couple steps. I know I have to distribute this 1/3 to both of my pieces inside, but at the same time, I know that we are going to undo the multiplication with which we have inside our parentheses. I'm going to treat this then as 1/3 times log of 100 plus 1/3 times log of x squared. I'm then going to have minus 1/3 log of y minus 1/3 log of z to the 5th. And I want you to be careful and pay attention to those negatives, because ultimately that 1/3 would go in front of this log here. So it'd be negative 1/3 that you're distributing to the addition when you're breaking apart your product. So be careful with the negatives. If you need to write more steps, please do so. Another thing we can do to kind of wrap this up a little bit is notice we have some exponents that we can bring to the front. In those couple of places, we'll have not only the exponents out front that we'll need to multiply, right, because it's multiplying in front of them, but also I have log of 100. We know that the base that is of log is 10, even if we don't see it, we know it's there. So I'm asking 10 to what power gives me, there's the answer. 10 to what power gives me 100? Well, we know that 10 to the second power is 100. So log of 100 is the same as 2, and 2 times 1/3 is 2/3. Plus, when I take 2 from my exponent and multiply it by 1/3, we'll have another 2/3 log of x. Nothing needs to happen with negative 1/3 log of y, so we'll leave it as is. Minus then 5 times 1/3 would be negative 5/3 log of z. And we have officially then gone ahead and expanded using the properties of logarithms. So this whole piece here is the expansion of what we did. Only skip steps if you are fully confident. Don't be skipping steps like I did unless you're fully confident what you're up to. It's okay to have as many steps as you need to make sure you're okay with them. Let's head to slide 4. I've got a few more examples that we can look at here, especially another kind of complicated one that we had, which might be useful for you. We have log base half of 4 cube root x squared over y square root of z. So we've got the division, we have multiplication, we have roots, we have a random base that we're working with here. So let's start off by, I don't have an exponent right away, so I'm going to get rid of the division utilizing the quotient rule. With log base half of 4 cube root x squared minus log base half of y square root z. At this point, I know that we have two multiplications here. So let's go ahead and separate them. I'll have log of 1/2 of 4 plus log 1/2 of cube root x squared. Well, it's before I do the x squared, excuse me, let's turn that x squared, cube root of x squared into an exponent. So we'll have x to the power of the inside exponent over the index. And this will be helpful for us in the next step when we use the power rule. So I'm taking minus, I'm going to subtract these pieces being added together. So not only am I going to subtract log base half of y, but I'm also going to need to subtract, when I distribute the negative, I'm going to also need to subtract log base half of z to the 1/2 power. So inside is the power of 1. Our index, even though we don't see it, is 2. So originally I would have, if you're not able to see why are those both negative, it's because I'm going to subtract log base half of y plus log base half of z to the 1/2. Oops, I can't get the half in there. So I would need to distribute this negative to both parts, is why it's coming up negative, if you need to see that extra step. I have some powers that I can bring out front, which is why we turned those radicals into exponents. But I also have log base half of 4, which could actually turn into a number. 1/2 to what power will give me positive 4? 1/2 to what power will give me positive 4? Well, I know that I need to have a negative to bring that 2 up front. And then 2 squared would give me 4. So x has to be -2. Because the -2 would invert this to positive 2 squared. And positive 2 squared we know is 4. Therefore, log base half of 4 is 2. Bringing out our exponent out front using the power rule, we'll have 2/3 log of 1/2 minus log of half of y. We didn't have an exponent there. We do have an exponent with our z, so minus 1/2 log base half of z. And now we have fully expanded our items. F is interesting because notice we have x squared minus 4. We don't have a rule for logarithms when we are subtracting within our logarithm. We only have multiplication, division, and power rules. I can't use my power rule here because it's attached to the -4 as well. But what we can do, since this is a difference of perfect squares, is we can factor this. This would then be the same as log base 117 of x squared, x plus 2, x minus 2. If you were to distribute that, we'd get back to the x squared minus 4. But notice now we are in multiplication, so we can actually utilize the product rule to rewrite this as log base 117 of x plus 2 plus log base 117 x minus 2. Depending upon what we're doing with logarithms, sometimes it's easier if they're in expanded form like we've been practicing, and sometimes it's easier when they're in their most simplified form with where we have started before expanding. On slide 5, our next examples are bringing and making them into a single logarithm versus expanding them like we've been doing. So now they're going to be an expanded form. How can we make them into a single logarithm type form that we would have started with? So on slide 5, we're going to start off with an example like we had completed on the previous slide. We have to make sure that our bases are the same. So just like when we were expanding, we kept the base the same throughout. If they're not the same, we might have to do a little side work to make them the same. And I'll show you how to do that in an upcoming example. Here we're subtracting. So when we're subtracting, we know that's the same as dividing. This is then the same as log base 3 of x minus 1 over x plus 1. There's nothing else we can simplify. It's written as a single logarithm, so we are done. Our second example, I have 1/3 log of 3x, or base 3 of x minus 2 log base 3 of y minus 3 base 3 of z. So they're all in the same base. The first thing I'm going to do is undo these by bringing the exponents back out front, because that's kind of where we left off with each one. We finished it off by the exponent rule. Now we have log base 3 of x to the 1/3 minus log base 3 of y squared minus log base 3 of z. I'm going to also work left to right. So I'm going to do these first two. They are subtracting, so we'll want to divide the insides. I'm also going to turn x to the 1/3 power into a cube root, because 1 will be the exponent and 3 will be the index. When I'm dividing, then I'll have log base 3 of cube root of x over y squared minus log base 3 of z. This tells me I need to divide. Ultimately, then this z needs to just move into our denominator because we're dividing some more stuff. So log base 3 of the cube root of x over y squared z or zy squared. Doesn't matter how you place it. But now it's written in one single logarithm. Example 6, or slide 6, I should say. Here I have both addition and subtraction into our example. I'm first going to use, I have got 2 log base 10 of y. So I'm going to move my 2 utilizing the exponent rule back up there. We still have log of x. Now we will have log y squared minus log of z. Even though we don't see the base of 10, we do know that they all have the same base. Starting from left to right, we can use the product rule to add these together by turning it into multiplication. We now will have log of xy squared minus log of z. The final part then is, because this is in subtraction, we can turn this into division to make 1 logarithm of log of xy squared over z. And I know I'm done because we only see 1 logarithm and everything is combined together as best as possible. All right. This is an interesting one, part D. because I have my logarithm on the left and a constant on the right that doesn't have a logarithm. But this is where some properties from the first slide will come in handy for us to rewrite this as a logarithm. I'm going to rewrite this first of all by taking my 4 and putting it back up with my x, so that I have log base 2 of x to the 4th power. And then I'm going to rewrite 3 as log base 2 of 2 cubed. As a reminder, looking back at that front page, if I have log base 2 of the same base, those ended up canceling each other out, leaving us with just the result of 3. So I'm reusing a property to manipulate it a little bit and rewrite it in such a way that now that I have 2 logarithms, I can combine them together. And we can combine them together since we are adding into multiplication. This then I know is going to be the same as log base 2 of x to the 4th plus log base 2 of 8. And then now finally combining them together as log base 2 of 8 times x to the 4th, utilizing our product rule. Let's try another one of those again, this time with the natural log, where I have the natural log on the left and I have a whole, or not a whole number, but a constant on the right hand side that doesn't have the natural log associated with it. I know that this is the same thing as saying -1 times the natural log. So I'm going to move that -1 back into the exponent. I also know that the natural log is the same as log base e. So I could say then that the natural log of 1/2 is the same as the natural log of e to the power of 1/2. Again, utilizing that inverse property. Utilizing that inverse property such that the bases are the same, which would end up canceling, leaving me with just the half that we need to match here. So really manipulating our items. And both these properties are on that front page under the inverse property list. All right, so rewriting this then, we'll have the natural log of x to the -1st power minus the natural log of e to the 1/2 power. We are in subtraction, so we know we can rewrite this into division, or the natural log of x to the -1 over e to the 1/2. And simplifying one step further, I know that if I have a negative exponent, that helps me move it to the denominator. I also know that I can turn my 1/2 power into a radical. So the natural log of 1, since nothing's left in our numerator, x times the square root of e. Everything is in its simplified form because we have one natural log and we combined them together. Typically, you will want to change your fractional exponents into radicals to keep things clean. Slide 7, our last slide, which we will be able to get through, is the change of base formula, depending upon if we start with an exponential function or a logarithmic function. So I have 2 examples of each that we can look at. We will use the change of base formula when we have our discussion tomorrow. So when I'm looking at 3 squared, I want to change this to base 10. Currently, my base is 3, and I want this to be base 10. So to transform this, I'm going to utilize the first bullet point because currently I have my base. So my a value in this instance is 3. Our x value in this instance is 2. And the base I want is 10. This is the same thing then as if I were to change this. 3 squared is the same as the base that I want to have to the power of our x value, which is our exponent, times log the base that I want of 10 times our current base of 3. And that's it. Like this is, oh, that scared me. This is the result. So I just changed it from a base of 3 to a base of 10. Leaving it in its exact form, not going ahead and turning that into a decimal, although it wouldn't be a decimal, it would still be 9. Because 3 squared is 9. If you were to put that into the calculator, you would still get 9 as well. Here I have 2 to the power of x. We don't have a power here, but I want to turn this into a base of e. So we're starting off with a exponential function. We want to turn it into base e. Currently, we have 2 to the power of x. This is going to be equal to the base that we want is base e. I'm going to take that to the power of my x value, which in this case just happens to be x itself to the power, times log of base e, the base that we want, of our current base. I also know that log base e is the same as the natural log, so I am going to say that this is e to the power of the natural log of 2. What if I want to go backwards? What if I'm given a logarithmic function and I want to turn this logarithmic function into a logarithmic function with the base of e? So currently we have log base 4 of 5. We want to turn this into base e. Notice in this instance, just when we're transforming it, the b is the base that we want to have. The x is coming from the of portion that we currently have over the base that we currently have. This is then going to be the same as log base e, the base we want, of 5, so what's currently in our parenthesis, over log base e, the base we want, of our current base. We can simplify as we know, since log base e is the same as the natural log. This is in its exact form. If you were to find whatever log base 4 of 5 is using the calculator, which would be an ugly decimal, and then you went and did the natural log of 5 over the natural log of 4 on your calculator, it would also be an ugly decimal, but at least you would be able to see that they are the same ugly decimals together. And then finally, the last example, we have the natural log. We want to change that base to base 10. So it's still the natural log, which is a logarithm. I know that the natural log of x is the same as log base e of x. So if it's helpful that you can see all 3 parts, we want to change it to log base 10. So log of 10, even though we don't see it, we know it's there, of whatever's inside our parentheses, over log base 10, even though we don't see it, we know it's there, of our current base. We know that log base e is the same as, we'll just leave that there. We'll stop there. We'll stop there. We'll stop there. So then this would be our exact form here. Each one of these. leaving it exactly as it is, not simplifying anything further with any ugly decimals or whatnot. So thank you again for letting me know that the sound stopped working so we could properly address it. But we did get through all of our slides, even though we did have that glitch. I will take that part out of the video when I upload it, so you don't have to sit through that part. But are there any questions